Hi, this is Math 2510, and this video is going to be the second part of sections 5.5 and 6.1. And it's mainly going to be the substitution rule that we're going to look at. Remember, with differentials, you have dy and dx, and they appear on derivative dy over dx. And we call them differentials. And so when we take the derivative, we get f prime of x, which is your dy over dx. And we can actually write that in a form dy equals f prime of x dx. And we call that the differentiation form. With the substitution, it's a technique that we use to convert some integral that's complicated into a simpler one that we can actually do. And so, let's say we start with the integral of f of x dx. We are going to let u equal some convenient expression, u equals some g of x, which is part of the integral. And then we're going to substitute that in so that we have the integral of a u du, which hopefully will be easier than using than the previous integral. So if we look at this, we need to know du dx, which is d prime of x, since u is g of x. So basically, if we take the derivative of u, we get du dx with respect to x. We take the derivative of g of x, we get g prime of x. And we use that to find what du is, and then we substitute both du and u in to our expression. The key is there cannot be any x left in the integral. We have to make sure we substitute everything. We have all x's into u's and our dx into a du. If that's not possible, then this method may not be possible. So it's not always possible, but it is a technique we use to simplify an integral. And the key is when we use it, well, that takes looking at the integral and realizing how this would benefit. So we have 2x, x squared plus 1 to the 30th power. If we let u equal x squared, then du equals 2x dx. Now, we have our 2x dx here, and then we have our x squared here. And so when we substitute, all x's will be gone. We will now have integral of u plus 1 to the 30th power times du. Well, not times du, but du at the end. And so we have the expression now completely substitute. This is something we can actually take the antiderivative of. This would be u plus 1 to the 31st power, 31, plus c. Now notice, if you would take this derivative, the 31 will come down and drop to a 30, and the 31 and the 31 in the denominator divide out to 1, so you end up with u plus 1 to the 30th power, which is what you have. And then that's the antiderivative. Now we don't have any limits, so we don't have to apply the limits. We'll get into that soon. Now we want to bring it back to our x's. This becomes x squared plus 1 to the 31st power of 31 plus c. So that is how you would do the u substitution. And we made something kind of complicated. Which, I mean, the long way would be to have taken x squared plus 1, multiply that out 30 times. That would have taken a long, long time. Then multiply all those terms by 2x. Then bring back together, because a lot of those things will be the same, x squared plus 1. You end up bringing back together into what we have. This is just a much shorter way using this technique. Right, so to use substitution, you need to choose an expression for u such that when you substitute u and du into the integral, there is no x remaining. If this is not the case, you can try a different u substitution, but sometimes you're just going to find out that you don't have an integral that can be a u substitution. And we'll see some of that. All right, so the steps, and it's kind of a general step. You make a choice for u. That's the hardest, one of the hardest parts, because you got to figure out what would work. You find du dx. Then you want to make sure you also solve for u, or du. So you want to know what your du is supposed to equal. Okay, sometimes that's not hard. Sometimes that is a little bit harder. And then you make the substitution and make sure no x's are remaining. Evaluate the resulting integral, and then replace x, the x's in your u's. So that way you have it in terms of x again. Alright, so we'll start with the integral of 10x plus 7 to the 4th. One of the things is knowing that something's a constant. When you take a derivative, it's 0. You don't really worry about the constants, but and so like for here, we let u be x squared. We didn't have to really worry about the 1, but letting u be x squared plus 1 would not have hurt us either. And actually, that may have even been a little easier. All right, so here we're going to do u equaling 10x plus 7. So du equals 10 dx. Now, nothing wrong with du equaling 10 dx, but notice we don't have a 10 in front of that 10x plus 7 to the 4th. We only have a dx. We actually have to solve for dx here. Dx equals du over 10. That way we can substitute in du over 10 in for 10x. So when we do that, our integral becomes u to the 4th over 10 du. Which, dividing by 10, that's not going to cause an issue with our antiderivative. It just kind of takes a long. So we do the antiderivative, which will be u to the 5th over 50 now, plus c. And then we substitute in what we had for u, which is going to be 10x plus 7 to the 5th over 50 plus c. Next one, we're going to let u equal 3x plus 5. So du equals 3 dx. And just like before, we don't actually have a 3 there. So we'll have to solve for just dx. We'll have du over 3. So we'll substitute everything in. It's going to be e to the u, du, that's over 3. Take the antiderivative. That's going to be 1/3 eu plus c. And now we can substitute in what we have for u. 1/3 e to the 3x plus 5 plus c. Now, if we were to take that derivative, the c will become 0, but the e to the 3x plus 5, derivative of that is itself, e to the 3x plus 5. But then you multiply by the inside derivative, which is 3, because of the chain rule. That divides with your 1/3, so you get what you wanted, the e to the 3x plus 5. If we take the derivative of that, it works itself back out to what we had. So one of the key things, and each of these is kind of a way. If you have a power, the u is going to be inside the power. Same thing with the exponent. A lot of times we make the u what the exponent is for exponential. This next one, we'll make the u a lot of times the denominator. So I'll do it this way. We'll let u equal 4x plus 7. Du equals 4 dx. And again, we don't have a 4 there, so we'll just solve for dx. We can only do that if it's a constant. And so now we'll let our substitution. So we'll have 9 over u du over 4, so 9/4 over u. Just waiting for this to save. And we can rewrite this. I'm going to take the 9/4 out. So 1 over u du. That's going to be natural log of u plus c. And so we'll end up with 9/4 natural log 4x plus 1 plus c. Then the last one of these four. We'll let u equal 4x squared plus 7. Du equal 4x, just 4x. And so dx. And then we don't have a 4, so we have to solve for the x dx. So x dx equals du over 4. So we can rewrite this. U to the 4th du over 4. And when we take the antiderivative, we get u to the 5th over 20 plus c. And we substitute in back what it's u, and we get 4x squared plus 7 to the 5th over 20 plus c. Notice in this last example, the x's all out, leaving only u's. We needed that x in front because of what that u substitution was. Right. So if we didn't have that x in front, we wouldn't have been able to do the u substitution. Or if we had an x squared in front, it wouldn't have worked out. We would not have been able to get all the x's out. And because, what we made is the 4x squared plus 7 is what we use to cancel it out. That is the key to knowing if we can do it or not. We decide on that u substitution and see if that cancels out the rest. So I'll do a couple more. So, for example, u equals x cubed plus 4x minus 5. Du equals 3x squared plus 4 dx. That is what we have on top, 3x squared plus 4. So this will work for the u substitution. So it becomes integral of du on top over square root of u, which I can rewrite that as the integral of u to the negative 1/2 du. Then I can take the antiderivative, you're adding 1, so it's u to the 1/2. And you're dividing by the 1/2, so that's multiplying by 2, plus c. And then you do the substitution. So you'll end up with 2 square root 3, x cubed plus 4x minus 5 plus c. So what looks like a really complicated integral actually turned out to not be that bad. Some with even trig. Here, we'll let u equal sine 5x. So du, when we take the derivative, we get cosine of 5x. But you also have the 5 come out from the chain rule, so you have 5 cosine of 5x dx. And so we would have to solve for cosine of 5x dx, since that's what we have, that we have to make the substitution for. So du over 5 equals cosine of 5x dx. And so now we can substitute in what we have for u and what we have for u over 5. We'll get u to the 7th du over 5. We take the antiderivative, we get u to the 8th over 40 plus c. And then substitute in what we have for u. So it'll be sine to the 8th of 5x 40 plus c. This is one way of doing it when we have trig. It doesn't always work again. So one of the things, one of the whole sections we do in Calc 2 is different integrals with trig. Here we have tangent x secant squared x dx. And I don't have it easy access to it, but let me just pull up the lit derivative of tangent x. Oh, that is secant squared x. So we know that, so we can use that. Okay, so derivative, I'll write this out, derivative of tangent x equals secant squared x. Right, so we'll let u equal tangent x. That way when we take the derivative, du equals secant squared x dx, which is what we have here. So this breaks down into u du, the simplest of u substitution. And so this becomes u squared over 2 plus c, which becomes tangent squared x over 2 plus c. But the next one, if we let u equal x minus 2 and du equals dx, we have a problem there. When we substitute this in, we'll have x square root of u du. There's no way to get that x out. Okay, so u substitution does not work in this case. And there's really no other thing that would make sense to try. We can't do Um, this has like letting it equal square root of x minus 2. That's never going to really work out. But even if we tried to do that, we're getting into having something like this, and it's just that's not helpful. So you can try other things, but when you don't have that much in the integral to begin with, um, they're really just it's just not possible in this particular method. Now with definite intervals, this is where you have limits, and really you can pick. There's going to be two methods. You can pick either method. There is no reason to choose one or the other. It's just two different ways of looking at it. You can do it whichever way you think is easier. Um, I guess maybe it's easier if one method makes you use pies, and it's easier just to use numbers. But or maybe if one has square roots involved where the other one doesn't, maybe there's a reason why. But it's going to come out either way to the same answer. It's still U substitution. What happens with these methods that change is basically the um, substitution and the limits. Do you re-substitute back in your x's and then evaluate the integral? Or do you evaluate the integral with new limits, then resubstitute in your x's? Actually, I don't even think you have to resubstitute at that point. You just evaluate your integral with new limits. You have to find your new limits to do that, though. So that's one thing to keep in mind. So method one, we're going to evaluate the integral by substitution. So in this case, we're going to let u equal x squared minus 5, du equal 2x dx. And we have an x dx outside, so we're going to let du over 2 x dx. And so we'll write out the limits. Now I'm not going to write in the limits. I'm just going to put an integral right now. And we'll have, let's see, u to the third over 2 du. Okay. Now, if you're doing it the first method where you're going to resubstitute back after you do the antiderivative, um, I would suggest you don't have to find the new limits, but do not write 0 to 3 because that's not true. So just leave it as an open integral all the time. We evaluate this, u to the fourth over 8. So 4 times 2 is 8. We won't do the plus c because we have limits. We resubstitute in the limits. So we resubstitute in your x. So you have x squared minus 5 to the fourth over 8. Actually, I gotta have myself. Hold on one second. No, I'm good. We're evaluating this at 0 to 3. I thought I jumped ahead, and I didn't. Alright, so now we're evaluating from 0 to 3. So we'll insert the 3. 3 squared minus 5 over 8. That's, of course, to the fourth power. Minus 0 squared minus 5 to the fourth power over 8. So that's 9 minus 5 is 4. So 4 to the fourth power over 8 minus, that'd be a negative 5 to the fourth power, which is going to be just 5 to the fourth power over 8. So let me get what those values are. 4 to the 4th power over 8 is 32. 5 to the 4th power is 625 over 8 would be 78.125. Which will give you a negative 46.125. Okay. Now we'll do method 2. And here we do find new limits. So we start with the same U substitution. And you find du, so 2x dx. And we're still even going to have to divide over the 2, so you have du over 2 x dx. OU substitution actually does stay exactly the same. That won't change in this case. So we'll have integral of u to the third du, and then that's over 2. This time we do want to find our new limits. And the way we do this is we plug in our 0 and our 3 into our u. So 0 squared minus 5 gives me negative 5. That 0 becomes negative 5. 3 squared minus 5, so that's a 4. And so when we do the antiderivative, we'll do u to the 4th over 8, evaluate from negative 5 to 4, which becomes u to the 4th over 8, sorry, 4 to the 4th over 8, minus negative 5 to the 4th over 8. Now that's the thing to realize is going negative 5 to the 4th, you have even power, so the negative still becomes positive. So this, and we had in the first part, becomes exactly the same. Okay, so this is still going to equal negative 46.125. So weighing to insert new limits, that can be helpful. I feel like that second method was the easier method to go about because it wasn't hard to get those new limits. If it's too hard to get those new limits, then maybe the first method's the way to go. It really depends on the problem. So we'll do a couple more. So I'll do one of each here. So u equals 2x plus 1. Du equals 2x 2 dx. We don't have a 2, so we have to solve for dx as du over 2. So we'll switch this to u to the 5th, du over 2. Take the entire u to the 6th over 12. And then we'll plug in 2x plus 1 to the 6th over 12. Evaluate from 0 to 1. We plug in 1, we get 2 times 1 plus 1 to the 6th over 12 minus 2 times 0 plus 1 to the 6th, 12. So 2 times 1 is 2 plus 1 is 3. 3 is 6 over 12 minus 1 to the 6 over 12. So let's do 3 to 6 first. 1 to the 6th is just 1. So 3 to 6 is 729. 12 minus 1 over 12. 728 over 12. 66.7. 60.7, sorry. Next one. This one now, replace the limits. Here we'll let u be, I'll do a different color. Okay. U will be 5x minus 1. du equals 5 dx. So dx equals du over 5. And so limit-wise, I'll do that here in a minute once I make all the substitution. So integral of square root of u over 5 du. And we'll do our limits. So 1 be 5 times 1 minus 1, which is going to be 4. 2 would be 5 times 2 minus 1, which would be 9. It would be 4 to 9. And to be honest, that may actually be the easier way, because you can see now we're going to be doing a square root. Even when we do the antiderivative, we'll have a square root involved. So, 4 and 9 are a perfect square, so it looks like it's going to work out to nice numbers. All right, so we'll do the antiderivative. This will be u to the 3 halves over 5, and then we got divide by 3 halves, which is multiplied by 2 thirds. Come on. Multiplied by 2 thirds. And we're going to evaluate this from 4 to 9. So I'm just going to simplify this a little bit. 2 to, do it this way. That 3 halves, that's the square root of u to the third power, and then that's over 15. I'm doing that way so we make sure we take the square root first. 4 to 9. So when we plug in 9, we got 2 square root of 9 to the third, over 15, minus 2 square root of 4 to the third, over 15. So square root of 9 is 3. 3 to the third is 27. So 2 times 27 over 15. Minus square root of 4 is 2. To the third is 8. So 2 times 8. 15. Which is going to be 54 minus 16 over 15. Which is, let's see, 38 over 15. I'll just leave it as a fraction. All right, so last problem in this, we have limits of pi squared to 4 pi squared. And this is for 1 over square root of x sine of square root of x dx. Now, we want to make sure we don't do the u substitution at sine of square root of x. That will not help, because you'll end up with a cosine for your derivative, and there's no cosine involved at all. So the best one here is to let u be square root of x. Take derivative of that, you get du equals 1 over square root of x dx. There'll be a 2 also, because you're taking 1/2 drops down, so you're dividing by 2, and then your 1/2 drops to negative 1/2. That's put the square root in the bottom. That's your derivative. Now, we don't have a 2 involved, but we do have the 1 over square root of x, so we'll multiply this by 2. So 2 du equals 1 over square root of x dx. So now we can substitute everything in. So I'm not writing in the limits just yet. We'll have sine of u, and then 2 du. And then we can take the 2 out. So 2 integral of sine of u du. Now we have to decide what's easier. Is it to find the new limits, which honestly in this case I think it will be. So to find the new limits, you're taking your square root of pi squared, which is just pi, and your other u would be taking your square root of 4 pi squared, which is going to be 2 pi. So from pi to 2 pi, which is not hard to do. Okay, so we'll take the antiderivative. We get 2 cosine u, and that would be a negative. Evaluate from pi to 2 pi. And so you have negative 2 cosine of 2 pi minus negative 2 cosine of pi. So cosine of 2 pi is just 1. So negative 2 times 1 minus, we'll make that plus 2. Cosine of pi is negative 1. So minus 2 is negative 4. So that ends up identical there. Alright, so that is the end of chapter 5 and going into chapter 6. The rest of chapter 6 that will cover 6.2, 6.3, 6.4 is going to all be on solving for volumes using intervals. So I'll see you then.